The second speaker is Duc-Minh Pham of Simon Fraser University. He will talk about a unique keyboard.
Hello everyone, my name is Duc-Minh Pham. Actually just graduated from Simon Fraser University. Wolfgang Stuerzlinger is my professor. So today I would like to present my paper, HawKEY, Efficient and Versatile Text Entry for Virtual Reality. The paper discusses the performance of current text entry solution in VR, proposes some noticeable improvement for them, and evaluates their performance. So first, let's talk about the motivation. So VR users always need to interact with virtual content. And nowadays, many modern systems popularly use handheld devices, such as controller, to allow users to directly or intuitively interact with virtual objects. However, to afford more complex and flexible communication between user and the immersive system, text entry is still necessary, especially in environments where text is relevant. A virtual keyboard is a widely chosen option because it is usable while standing, and it can be implemented easily. Then the question arises, what is the performance of current text entry solution? What are their issues or limitations, and how can we improve them? Okay. Let's see some situation in which text entry is necessary. So in VR, controllers are suitable for simple input, like selecting a menu button or manipulating the position of virtual objects. However, they are insufficient for large amount of data. Imagine that you want to chat with your friend in a VR game, or type some sentences in a text editor, or enter a URL in the web browser. Then you definitely need a keyboard. So many modern VR systems implement a virtual keyboard. Users typically manipulate the controller to select the keys with raycasting or room light methods as proposed by Google Daydream. Typing on the virtual keyboard is still a hunt and peck style, and its lack of haptic feedback. Therefore, effort has been made to utilize a physical keyboard in VR. VR headset prevent users from seeing a physical keyboard. However, novice typists usually need to take a look at the keys. Some uncommon keys like the curly bracket or the vertical bar are even hard to find for experienced typists. In addition, previous studies have shown that visual feedback help users reach higher text entry performance than solely haptic feedback. Therefore, physical keyboard and user hand should be represented in the virtual world. Previous studies have proposed some method to track and visualize the physical keyboard. They use Grindex or some special cover to extract the keyboard easily from the scene. Alternatively, they track the keyboard and user hand with markers and display corresponding virtual representations. These methods require some significant modification to the keyboard or user environment. So in this paper, we use only an RGBD sensor to capture the keyboard for fewer modification and easy setup. So this is our design. So we just attached the Intel Ryzen D435, which is an RGBD camera, to the HTC Vibro. Because virtual keyboard can be used while standing, we also propose a portable keyboard design, not only suitable for high-speed text entry while standing in VR, but also usable when sitting or walking in VR. So this is our design. So you can see like it includes a surface where the keyboard rests on and two adjustable straps, which help to stabilize the tray in front of the user body and parallel to the ground. We call this design HawKEY because of the similarity between it and the hawker tray. The tracker is only attached to the keyboard to track its position in some condition in our experiment, but it is generally unnecessary. So HawKEY can also be used while sitting or walking around. And these are the results from previous studies that utilizing a physical keyboard in VR. So you can see that the last study achieved the highest result with 67.2 work per minute in baseline and 69.2 VR in VR condition. This study also used all of these studies all use lowercase characters in their experiment, but it is not always the case. For example, URL consists of like slashes, colons, and sometimes ampersands. Hence, in this study, we want to see how unfamiliar characters affect the typing speed and typing errors of VR users. So here is our experiment. So there are two factors in our experiments. The first one is the text complexity. So it has simple sentences that include only lowercase alphabetical characters, and complex sentences may contain uppercase characters and some other uncommon keys. And there are also 6 interfaces, and we want to identify the most beneficial keyboard visualization methods. So these are 6 interfaces that we use in our study. So the first condition is baseline, so just investigating normal typing speed of participants in real world. The second condition is none. Participants enter text in VR without seeing the keyboard. So this condition serves as a VR baseline condition to examine how typists perform when the keyboard is not visible. Hand was visible as a 3D point cloud in this condition. So the third condition, the frame. In this condition, we visualize the keyboard as a rectangular frame. So basically, participant knows where the keyboard is, but they don't see the keys. And in this condition, the hands are also visualized as a 3D point cloud. In the next one is the model condition. So in this condition, we show a virtual keyboard models that matches the dimension and appearance of the real keyboard, and participants can see the hand. So by mixing the virtual and physical content, we aim to discover if this combination is beneficial for typing speed or not. So the videos, we use a camera to capture the 3D video of the keyboard and visualize it at the plane in VR. And finally, point cloud. So this is just pure 3D point cloud that we constructed from the data from the RGBD camera. So this is 6 conditions that we examined in our study. And this is an illustration of the text entry task. Participants always did the baseline condition first. Then, 5 VR conditions were counterbalanced. And this is the real setup of the experiment. The left is the baseline, and on the right is what participants could see in VR. So this is an example of a simple sentence with only lowercase characters. So result and discussion. So there were 16 participants in our experiments. 6 of them were females, and they all have limited experience to VR. That means they have never tried VR before or only tried it for a few times. And this is the data that we collected from the experiment, including objective and subjective measures. So for the first, we go for objective measure first. So the entry rate, when it was per minute, we count the number of transcribed characters in a minute. So with simple sentences, there was no significance between conditions. With complex sentences, the baseline, of course, supported higher typing speed than all VR conditions, except the video. No significant difference was found between VR conditions in the case of complex sentences. Next, we measure how fast and accurate participants could enter the first character. No significance were found, but we can see that the video and point cloud seem to achieve higher first character correctness comparing to baseline. So we can see here video and point cloud is comparable to baseline, but no significant difference. Reviewed by ANOVA. Now, take a look at the error rate. So the first error rate that we use a keystroke per characters, or KSPC, is the ratio of number of keystrokes and character in the transcribed text. Now, the difference between VR conditions becomes clearer, where the video and point cloud achieve smaller KSPC than other VR conditions. You can see here. Baseline, as expected, resulted in smaller KSPC than all other VR conditions in the complex sentences condition. The second error rate is the erroneous keystroke error rate. Investigate the rate of incorrect fixes. That means when they type something wrong, they fix it, but they fix it wrongly. So that's the erroneous keystroke error rate. Again, with complex sentences, video and point clouds resulted in smaller erroneous keystroke than non-frame and model. Finally, the last error rate, which is the total error rate. It is the ratio of the total incorrect fixes over the total of correct and incorrect characters. Here we can clearly see that there are 3 groups of conditions. So the first group, baseline, which resulted in smaller error rate than all other VR conditions. And the second group is the video and point cloud, and it still delivers smaller error rate than non-frame and model. At this point, we can see that although the video and point cloud did not help users to significantly improve their work per minute, but they did help typists to reduce the number of errors. Now let's take a look at some of subjective measures. So we asked participants to complete national TLX to access their perceived workload during text entry tasks. So the result indicated that non-frame and model cause significantly higher workload than video and point cloud. Ease of use. Yes, again, we asked participants how easily they could get familiar to each of the interfaces. The result indicated that non-frame and model were harder to use than video and point cloud. We also asked participants how likely they would use each interface for VR text entry. So post-hoc tests indicated that video was significantly more preferred for VR text entry than non and frame. Point cloud will also receive significantly higher rating than frame. You can see here. Okay, so now some discussion about, we also analyze if our participant group were biased toward experienced or inexperienced typists. For this, we compare the participant work per minute in the real-world baseline condition. And a Shapiro wheel test could not reject that my participant came from a normally distributed group, as you can see here. For complex sentences, the appearance of uncommon symbols like punctuation and the need to use the shift modifier key significantly reduce typing performance in all metrics. You can see here. So this is the work per minute in the complex condition, which is lower than the symbols in the simple sentences. Hence, we could divide the participant group by the means of work per minute in the baseline complex condition. So 50% of our experience of our participants are determined as inexperienced, and the other 50% were experienced typists. By dividing the participants into inexperienced and experienced groups, we could compare my results with one of the best solutions in previous studies. So the experienced subgroup type 67.1 work per minute in baseline condition and reached up to 77 work per minute in video condition as compared to previous work. So to gain a clearer picture of the difference between inexperienced and experienced typists, we also perform between subject ANOVA on work per minute and total error rate between the baseline condition and VR condition. And ANOVA revealed that experienced type significantly faster than inexperienced in all conditions. However, they seem to make the same amount of errors. That means that the experienced type faster, they make same amount of error that when compared to the inexperienced, but they tend to fix it faster. Finally, here are some comments for the design of HawKEY. That HawKEY is very good to type on. The prototype is generally comfortable to wear. Keyboard straps were a little uncomfortable, and the participant wanted to move the keyboard a little bit further from the body. So we acknowledge these comments. And so, in this paper, we propose HawKEY, text entry solution suitable for high-speed text entry while standing in VR, but also usable for sitting and walking. We identify most beneficial keyboard visualization methods with video and potentially point cloud that allow users to reach the typing speed as compared to the baseline condition. And we examine the effect of unfamiliar characters on text entry speed and error rate in VR. So for future work, although the current design improves text entry in VR, it also introduces a conflict when users want to interact with virtual content using controllers or other devices like the pen. So our current solution is to make HawKEY quickly retractable so that it won't collide with the controller when they are in use. In addition, we can add holders to both sides of HawKEY to store the controller when they are not in use. Okay, so this is the end of my presentation. Thank you very much.
Is there any question or comments? Yeah.
No, it's okay. Did you check for latency between the video feed, the point clouds, and the different methods? Because I can imagine if you're looking for words over the span of 1 minute and typing being like pretty fast on the keyboard, reorienting this helps a lot, especially if you're not such an experienced typist, was there a difference between the video feed and the point cloud in terms of the latency until the user can perceive what he's getting?
Oh, you mean the latency in the visual feedback?
Yes.
Oh, yes. So actually, we did not really measure that latency. Yeah, but based on experience, it seems to be not different. But of course, I need to measure it carefully. Yeah.
Thank you.
Yeah, please.
So it makes intuitive sense to me that the none feedback and frame feedback would be bad, and that video and point cloud would be good. But model seemed not to work as well as I might have expected. Can you speculate on why people did not like the model feedback condition?
Oh yes, because based on our base, because we also asked participants they comment about the model condition, and they said that okay, because it's a combination of a virtual thing and a real thing, sometimes the point cloud is not that good. That means at the very end of the finger, they could not see it clearly. So it's a mismatch between the virtual and the real thing. So that's why it reduces the work per minute. So in the future, if we have like a better sensor, it would be better.
Okay, thank you.
Any other questions or comments? Well, please. Do you need the mic?
I'll be fine. So, as someone who does a lot of virtual reality gaming, the idea of having another large peripheral strapped to me is a little concerning. Have you had any thought about how you're going to make it ergonomic, I suppose, given the wide range of motion that someone will probably want to do conventionally in VR, and then maybe pause to type something without having to go through quite a bit of setup, I suppose?
Oh yes, so this is the first effort. We want to make it retractable very quickly when they don't need the keyboard. And of course, if they tend to move very quickly, we really need a flexible frame that allows to do that. Yeah, so this is just the first improvement. We will try to make it better and better in the future. Thank you.
I have a question. Yeah, this is very trivial question. Well, to me, the current implementation is bit, how to say? It seems to me the strap is annoying. So if you use this method in real applications, maybe it is bit not so good in usability issue. So how can you improve?
Yes, and an effort to eliminate the straps. So this is one effort. Of course, we did it a bit stabilized. So we try to move the strap to the back of the user, so they can hold the strap like this. So it does not prevent them from freely move the head. Yeah, so this is our solution. Yeah.
So how stable does it need to?
So we try not to move the strap like this. It should be come from the back, and it should be like one strap here and the other strap here. So it helps to stabilize the keyboard, and the keyboard should be chosen so that it's light enough to be handled as stable as possible on the back.
Well, I agree with the purpose of this research. Because I'm from industry, so text input is very important function in real application. Yeah.
Yeah, so that's one of my professor want to make a real product for this one, so that VR user can quickly type on the keyboard And they also need to, yeah, seeing the keyboard in VR is, I mean, it's important in some case when in the future we have visual analytics in VR. We need to in-game chat to chat with other people in the game. Yeah, so that's our direction.
Thanks. Any other questions or comments? Very well. So let's thank our speaker again.